Welcome everyone to another episode of Mechanisms and Mentorship with your host, Rafael Testai. Today we have another very special guest, Ruben. So Ruben, why don't we go ahead and dive right into the problem. What problem were you trying to solve? What's the big picture?
Yeah, so the customer approached us. They had a product. It was a training product for selling to their customers where they took a rifle, changed out some internal parts, added their own magazine, and it was pretty much an air-powered rifle for training purposes. So this is new product development. The customer came to us and said, hey, we want to test this out, make sure everything's good to go before we start handing it off to customers. So this particular fixture is a testing fixture that is supposed to fill the pressure vessel with just compressed air at a very high PSI, 3,000 PSI, which can be very harmful to people if any kind of catastrophic failure occurs, and activate the weapon without any human interaction. The only human interaction is loading the weapon, setting it up, and then hitting go on the start test.
So part by part, first I want to make sure the customer didn't come to you to design a rifle. They already had a rifle, right?
Correct, yeah. They could pretty much take a rifle off the street or for law enforcement or some type of military application, and then they'll add their parts to the rifle, plus they also sell this, what they would call a magazine.
Okay, so they have a rifle, they have some different components that they can interchange, and what exactly do they need your help with in that process?
Our responsibility was designing the actual test fixture so they can get some type of certification so that the customers are happy and they can prove to the customers, yes, this is a quality product. Here's our testing data that we've done X amount of rounds for X amount of time on X amount of weapons. So
basically they need to test repeatability on the device, that its predictable repeatability is the same. What you buy today is the same what you buy tomorrow off the shelf, right?
Similar, more of proving out their mean time to failure in terms of reliability. So proving out the reliability that they designed for. Specifically to this, the particular weapon we'll be looking at today, they wanted to shoot 175,000 rounds, and each cycle's 30 rounds, so that's just under 6,000 cycles of testing for a single weapon.
I see. Well, personally, I don't know a lot about weapons and guns, so this is going to be a lot of a learning experience for me. But if you're a big passionate about guns and shooting ranges, give this video a thumbs up and continue to watch. And even if you're not like me, you're going to learn something today. So can you pull up a picture of what this gun looked like? Is that possible? A similar gun, not the exact gun.
Of course.
Something on Google Images.
This is just Google shooting AR style rifle.
Okay.
Or more, if it's a military type of application, it's a M4 rifle. But this is the type of rifle we were testing. For civilian purposes, it's a semi-automatic. Military application, they have full auto. So we were testing the full auto version of this type of weapon. But this image, I'll get back to it in a little bit, but this is the type of rifle we'd be inserting into our test fixture.
Looks like a free body diagram from statics.
Exactly.
So now that the viewer understands what problem we're trying to solve, let's take a step back and start again from the beginning and slowly start diving into some of the details. So how does a senior mechanical design engineer like yourself approach a design problem? Do you have specific process you follow? If you could break that down for us, if you want to use the whiteboard, if you want to show us visuals, and by all means, this is not exactly what the company that you work at right now, Pipeline, as you see on his chest, and this is the Pipeline podcast room that we're recording in right now, but more of like what's your personal process when you approach a problem in design, if you want to share with us?
I think I approach it around the same way most engineers are taught to approach problems. I like to fully understand my parameters and constraints. Sometimes, if it's a fast project or more in the industry we're in, right, where we're trying to position ourselves to be fast and dynamic as a company. But I personally like to approach problems by breaking them down first, the analogy I like to use is breaking down a number into its prime numbers. So understanding really what are the blocks that we need to figure out and solve Once I have those, if it's a multi-person team, each of those building blocks, quote unquote, can be assigned to each person, and it kind of naturally breaks down in sort of subsystems.
Okay.
We'll see that in the future, or in a little bit, rather. And from there, typical product design cycle where you do some concept generation, mostly just kind of cartoons, whether it's a sketch on a napkin, just cartoony blocks in CAD.
We have a lot of napkin sketches in the back. I'm just kidding. But I think this reminds me of a theme that I've been seeing that a lot of people have mentioned to me, that in engineering school, they don't teach you everything you need to know, but you learn that as you go afterwards. It's an introduction. But they do teach you how to break down a more complex problem into something simpler, like you were describing. Would you agree with that?
Yeah, I would agree with it. Even, you just brought up a statics class. Even there, the first thing you ever do when you're, even doing a homework problem in statics or problem on test is make a free body diagram, right? That's really breaking down, okay, what are the forces that are acting on my body? What moments I need to take into account, and really understanding the basic fundamentals of what you're trying to solve.
I'm smiling because I'm excited as to how what we learn in school in statics translates to the real world, developing real products and making real money. So I'm excited. So yeah, if you want to just walk us through a little bit more of this process of yours.
Yeah, for this specific problem here, I'll bring up that image first. Maybe I can hide some stuff and give you a little preview as to what we did, and you'll see some analogy. So one of the requirements our customer presented to us was, hey, we need to be able to hold this like a person holds a rifle. So that means you can't just bolt it down to a plate and hit the trigger. The internal mechanisms of the rifle, the way it's designed, won't allow it to properly cycle. So
what does it mean to cycle?
To cycle, if you're shooting a typical rifle, means that you can chamber a round. So you put a round into the chamber, you close the chamber, you hit the firing pin, explosion happens, the bullet goes out the tip of the barrel, and then you eject the shell, which is the brass you usually see. Does our image have it? You can see it right there, that little shiny piece in front of all the black. That's the brass being ejected, or the shell being ejected. And then you insert a new round within that mechanism, and that's one cycle.
Okay.
You shot one round. That's what I mean by cycling the weapon. Here, when I just mentioned those cycles a while ago, I meant shooting an entire magazine, which is 30 rounds. For our test fixture, that was one cycle. So I guess we're trying to keep all our ducks in a row.
Oh, thank you. Thank you for clarifying these terms. I'm following. Okay.
Yeah. But for this, since it's an air-powered rifle, we're not ejecting anything. The internal mechanisms are just allowing, when one cycle or a round is shot, is just letting some air out of a pressure vessel and doing some type of counting, and then be ready to shoot, quote unquote, the next round.
Okay, right on. So if you guys want to take a closer look here, there appears to be a gun there, right, in the CAD. Did you design this gun from scratch as like kind of cartoon CAD to put on there, or no?
Right, that's an option.
Yeah.
Sort of almost reverse engineering, if you will. Fortunately, one of our team members was able to find a rough model. As you can see here, it's sort of the handguard, the barrel, the excuse me, the grip, the stock, which is this area back here that bumps up against your shoulder, your control area here, or your control group, which is your trigger, a button to release the magazine that'll pop out of here, and then your safety and firing selector, which is on the weapon we were using. It'd be safety on, which is a safe weapon, semi-auto, and then full auto. That's what that orange circle represents. But you can see it's, like you've very much said, it's a dummy character that we can only approximate so much. In this specific example or customer, it was just difficult to get us a product since they were adapting to something that's already out there on the market. So they don't particularly have the actual CAD models. They kind of have to do some reverse engineering, and we kind of get a version of that.
So it sounds like one of your team members, they downloaded this file from somewhere. Is that right?
Yeah, you can download it now.
Yeah.
I think it's on GrabCAD or something like that. One of those file sharing sites.
Well, look at that.
But It was one of those things of trust but verify type of thing. So there were some things that were off, but it was good enough. It was a good representation that we could design around and have a conversation around.
Yeah, and who knows how many hours it saved you from having to reverse engineer a gun too. It's
Correct.
Good enough. All right, so you have the gun in the center, as everyone can see. What else?
So if you can see here, we're doing some type of contact here up in the handguard area where you put your offhand. Your hand would be here in your control group holding onto this pistol grip, and then the stock would be up into your shoulder. If we go back to the free body diagram, that's exactly what I just described, right? The stock is into the shoulder. He has control of the firing with his right hand. This is a right-handed person shooting, and then he's controlling his rifle with his left hand, his offhand, here up front near the towards the end of the barrel. This is a fairly long barrel.
So in terms of statics, you would say that this has 3 support points. Is that what you would call it?
I would say 2 support points. Your right hand isn't really supporting. You don't control the weapon with your right hand, like where you point the weapon. It's more your left hand and into your shoulder. So that's why I have sort of this. It's quasi free body diagram, but some type of pin joint here and some type of pin joint there. I guess you could theoretically put a moment there because your hand's not going to twist it. But the important thing to understand is you're going to get some recoil up just based on the moment from your grounding positions here and here, and where your force is being exerted, your reaction force, I guess, from the explosion of the bullet.
Very nice, very nice. I wonder if we have some math laying around, like how this one translate that to the math, and then decide if that was even needed to solve this problem. I don't know.
I can walk you through it. A colleague of mine actually did some of that background math. So ballpark numbers really is estimating the amount of energy sort of stored or potential energy from the explosion, and then translating that to how fast is this mass going to accelerate backwards. That's going to give you a reaction point here, a moment reaction here, or 2 forces that will give you a counter moment to the moment that's being experienced by the reaction force that the weapon is exerting onto the person.
By the way, this is so unfair. I didn't tell Ruben that I was going to ask him questions about math, so he handled that beautifully.
Nah, no problem at all.
All right, so let's continue with the cal. What else do we have there?
Yeah, so like I mentioned before, I guess I'll talk to the things I personally designed. So that's the weapon mounting system, which would be simulating the hands that are actually holding the weapon rigid, quote unquote. And then another colleague designed actually activating the weapon and interacting with the weapon. There's a couple steps that we needed to do to the magazine itself to reset the counter that was on there. That's what another colleague designed here. That's a little interesting, but pretty much the idea here, I'll swing around the back, is we pretty much said, we need to not put too much mass on this weapon in order to simulate like a person holding it. So we said, how do we activate or act upon the control features of the weapon, being the trigger, and got to push a couple buttons, that kind of thing. Said, we can use some sort of pull string type idea similar to the brakes on a bicycle, where you pull on something and you can act on the force with something else. So that's the sort of technology, if you want to call it, or ideology that we went through. So here you can see a little bank of pneumatic cylinders and some pull wires here. So as you pull the wire back, you'll act upon the weapon somewhere out here. So that allows us to have the weapon kind of move around and be sort of flexible, but not adding too much mass, right? Because I guess if you wanted to brute force this, you could put some pneumatics right onto the weapon itself, attach it, but then you're not really simulating a person holding it.
So it sounds like a lot of teammates worked on this, and I wanted to ask you, how do you manage a good collaboration? Because there's a lot of people working on different parts. Any tips for anyone listening?
Yeah, I think it goes back down to that process that I described, where you're breaking down things to the primary numbers or the primary blocks, right? And identifying the subsystems that are part of what you envision your final solution to be. So here, I just went through a couple of them. One of them being this magazine resetting mechanism, the what we call the hand of the weapon, and then the mounting systems. And finally, the third thing would be sort of the frame, which keeps all the operators safe, since again, it is a pressure vessel pressurized to 3,000 psi.
Beautiful. All right, let's see. What's your process of conceptualizing a new mechanism? Like, because there's several ways to design mechanisms in SolidWorks, layout sketches, top-down modeling, master part modeling, but I find it sometimes challenging to design something in SolidWorks where it's going to be moving. How do you do this?
For me, I personally, I prefer a combination of bottom-up modeling and top-down modeling. When I'm conceptualizing, I'll have some type of master model. I kind of, just to conceptualize, it's quick and dirty, right? It's all just blocky extrusions. And then once I get into the refinement of things, I'll break those out into separate parts, or even just make a new part file entirely, and then put it back together, build it up, and then, once I'm making refinements of that design, I can go ahead and make changes in context within an assembly, which is very much a common practice when you're doing top-down model.
So if I understand this correctly, so you start with master part modeling, which is a part file that you have several bodies inside of it, right? Master part.
Yeah, sometimes it's a multi part body, yeah.
And then it's just quick and dirty. You kind of see how things fit with each other, and then maybe you do a save bodies command. You export these bodies. No?
Not all the time. Sometimes.
Sometimes.
It depends, again, how granular I get with the detail. Sometimes it's enough to just say, okay, here's the idea. Other people saw it. My team members say, okay, yeah, that looks good. Let's keep going. Then sometimes, if it's obvious enough, I'll use it. If it's a little more complex than that, right, because we're just saying, this body slides on this other body, then it's a little easier to make an entirely separate part file and break it down that way.
Okay, so if you have different part files that came from the master part file, then you import them into an assembly, and you see how they fit and move with each other, and then you start making edits to the parts within the context.
Correct.
Right?
Yeah.
Okay. That's I was able to follow that all along. Perfect. I hope. Give it a thumbs up if you're able to follow that. If not, leave a message below and we can make a follow-up video on that. I can explain that. Could you show us how you modeled a mechanism in SolidWorks to accomplish the desired output?
Yeah, we can jump right into sort of the weapon mounting system. I already have some sub-assemblies open. This. So this is the rear one.
So this is what's on the shoulder, basically?
Yeah, this is simulating the shoulder. That's preventing the weapon from moving down. It prevents it from rotating about the Z-axis here, which is the same coordinate system we used for the weapon, trying to keep everything aligned. So the weapon would be fastened here, some quick straps that would keep it in there, make it easier on the operator, since they might have to take it out every so often to do maintenance on the weapon and things like that.
We always keep the operator in mind.
Exactly. So typical tree organization is I like to have my assemblies and what I call made to spec parts, or custom parts that I specifically model, or if I'm taking an off-the-shelf part and having that modified, I consider that a made to spec to my specifications part. I'll have that above, and then I'll have any hardware or off-the-shelf parts in folders below. It's easy to organize. It's easier to organize it that way for myself. I try to keep most of my assemblies in that sort of ideology. This project actually took place when I was beginning to adopt this, so you'll see it if I open up some other assemblies where some of them might not have it. So I was starting to kind of dip my toes in that organization method.
So you designed all this, or one of your teammates?
Yeah, this was all designed by us here at Pipeline. My teammate designed. So this shock, for the most part, is an off-the-shelf assembly. A teammate designed these 3 parts that allow us to put a spring on the shock, so it's a typical shock or strut on there, and that'll absorb the energy from the rifle that's in the Z-axis, which is the impact on your shoulder.
All right. Perfect. Let's see. Next is, can you give us 2 golden nuggets on how you modeled this mechanism? The more specific, the better.
Yeah, I think the first one would be, here you can go to another part, or I can describe it a little bit. You see all these pink panels? They're all the same but different, right? So here was a real good exercise in using a design table and configurations. I've used configurations in the past, they're always handy, but I can open up this guy. I should have it open right here. But here you can see I already have all my faces kind of done.
On the top left.
In the top left in my feature tree area. So I have all my faces. Let me expand the names. You know, bottom top, face forward, right, left, back, front. These are descriptive names, but you know, I was able to tag these up and really make quick changes. You know, I realized, oh, we need to make it slightly wider. You know, I'm just changing a few numbers here and there, trying to make the development process more efficient. You know, teaching myself a new feature to use in SolidWorks, that kind of thing. Definitely something to check out.
One thing that has given me trouble in the past when using configurations is it helps me to right click it and make sure I suppress certain modifications on the other configuration, because otherwise it becomes a mess. Has that ever happened to you?
Yeah, no, most definitely. You know, I know exactly what you're talking about, where you kind of design something and then you realize, oh, I need to make multiple configurations, and then for your second configuration, for example, you like add a feature, but then that feature is potentially unsuppressed in your original configuration.
Such a headache sometimes.
Yeah.
It scares me a little bit.
That's why, you know, I try to design like this panel. I try to incorporate all the features that I anticipate I would need. You know, obviously that's an ideal. You're not always going to do that. But I knew for these panels, I needed some bolt holes to mount things, and then I needed to mount this view in a window. This panel's actually upside down. There you go. You know, so these are all features I can suppress or unsuppress, and you know, try to set up my sketches for my holes such that it's not dependent on the size, but more, it's all relative to the geometry of the overall panel.
Next question is, what was the hardest part about developing the mechanism inside SolidWorks? Can you open the design and roll a feature tree back, up and down? The more specific where you encounter this obstacle, the better.
Yeah. Some trouble that I had was, and potentially this is more due to the machine I was working with at the time, was on this enclosure frame itself. As you can see here, it's a lot of detail, right? It's a lot of lines that have to be rendered. So
Can you do maybe hide the solid body so people can appreciate all the sketches in the back?
of course.
Yeah.
Yeah, so this is easier for SolidWorks or in my computer to kind of handle and render. It's easy to visualize. There's not properties with volumes and things like that. That was easy to draw, right? When conceptualizing this and talking to other teammates, it was easy to kind of get the sketch, throw some, here you can see the structure system, so everybody's on the same page. Other people that needed to design other subsystems have something to reference. But as this, you know, as we continue development on this, teammates be like, oh, I need a member here to mount this. I need a member there to mount this other thing. You know, you can see it looks simple, right? It's pretty much a box with some lines going across it, but there's potentially some complexity to it. So as you go and you start rendering these parts, my machine started slowing down, you know, that led to some frustrations on my end, type of thing. So a workaround that in the future that I'll likely implement is, instead of using this complex geometry shown here, I could just show a dummy version of this, right? I understand what aluminum extrusion is. I understand how to work with it. So there's no need to have all this detail in there that is really just eating up computer memory.
I see, but isn't that an 80/20 downloaded from a website?
No, this is using structures or weldments if you're familiar with it. So you can.
I don't have a ton of experience using weldments, so for any of us that don't have a ton of experience, quick just summary. Okay.
Yeah, of course.
Okay.
A weldment is pretty much what you see here, where you can make a wire frame. So if you're making like a table, some type of frame for an automated machine, this is a very much clear example of that. Or you need to hold something that's cantilevered, and you're going to use, some square tubing. It's not just aluminum extrusion. You can use the structures or weldments to kind of organize your files. That way, you're not making. Here, roll this back. You're not going to the 8020 website if that's the aluminum extrusion you're using, and downloading this 1.5 by 3 inch member that's X amount of inches long. Then you have to download another one that's different. This allows you to take this cross section as a sketch itself and apply it through where you see each of the splines up here. You can specify which line will be with which cross section, so SolidWorks will automatically make those extrusions.
Where do you get the cross sections from? Is there a library in SolidWorks that has them?
You can make your own. SolidWorks comes with some that are typical. If it's a ANSI inch ones, it's nominal stock material for rectangular tubing. That's very much a popular option that people use the weldment feature for.
Okay.
But there's always ways to add your own. You can just go download, if it is a different type of extrusion that you need, you can download it, save the sketch as a sort of template. There's plenty of resources online that show you how to do that.
Okay, perfect. So you're showing us that the better way now, looking back, is maybe you didn't need all those cross sections, all that detail. Is that right?
Not necessarily the cross sections. I think the cross sections are important, but the detail of each body is not needed. We don't need to be that refined in order to get what we wanted to get out of this frame. And the frame was just having mounting positions and space claims that people could not intrude on. So
basically, it would just be some more blocky extrusions with less detail, right? Less cutouts.
Correct. Here,
Okay.
I threw some examples in preparation for this podcast. See how this is void of any detail compared to the cross section up here. There's no hole in the center. There's no fillets. There's no internal cutouts. Things like that. Down here, it's just a block that's the nominal size. We do have a hole, but there's no internal cutouts. That's all memory that my computer doesn't have to generate. So, like I said, this isn't super complicated. It was a little heavy for the machine I was using at the time, but if you're designing an entire frame for, say, an automated manufacturing line, then it gets cumbersome on your computer. So having less detail there is going to save you a whole bunch of memory and allow your machine and yourself to work more efficiently.
Well, wonderful. Is there anything that I haven't asked you that I should have asked you, Ruben?
Let's see. Something important for this design that had to be taken into consideration was keeping people safe. We touched on it earlier, where school gives you sort of the baseline of what you need in order to be able to go out there and solve problems. Sometimes it'll happen where it's a static type of problem where you can easily go back to your notes or a homework problem that you remember that's analogous to it and say, that I remember solving it this way. This applies to this, right? For this, I had never really done a calculation where you convert the stored energy in a pressure vessel into the forces that these panels would experience in the case of a catastrophic failure. So the pressure vessel failing and an explosion, pretty much. So I had to go out there, do some research, read some papers, verify some sources of where I was getting these equations, and really applying my basic knowledge of pressure vessels and conservation of energy and conservation of momentum, and applying those basic principles that I learned in school to a much more complex problem.
And is there ever any, this is a very honest question, like, do you ever have any doubt, even when you do something new, it's like, can I have this verified by somebody else? Do you ever ask yourself that?
Absolutely.
Yeah.
And that's part of the development process, right?
Okay.
No one's perfect. we're all humans. Some engineers are better than others at seeing some of the things they might potentially miss when they go and check your work, right? But it's as engineers, we always want to include that factor of safety, and part of that is having someone else verify your work. A quote that I always go by is trust but verify. I know I've mentioned it before, but that way you take it for what it is, but you still kind of make your own sort of back of the envelope calculations and say, okay, yeah, that checks out. That's ballpark of where it should be.
Trust but verify. I like the way that sounds. Well, una pregunta en español para Rubén. Le quiero preguntar, ¿cuál es la parte favorita de ser un ingeniero mecánico?
A mí me gusta crear algo que nadie ha creado. Nosotros estamos en un negocio donde un cliente viene con nosotros y dice, quiero hacer esto. Y nos presentan ese problema porque nadie ha creado la solución para resolver ese problema. Así que cada vez que entrego algo es algo que nadie ha hecho. Me gusta cuando el cliente está feliz con el producto y es emocionante ver al cliente sonreír cuando miran que algo funciona como debe de funcionar.
Sí, es muy divertido. Diseñar e innovar se siente como que uno es un chico y nunca creció.
Exactamente.
Así que es divertido. Bueno, muchas gracias. Thanks everyone for watching. Please stay tuned. Until next time. Rafael Testai, Ruben.
Thank you.
That went great, man.